All right, welcome back to our 9th episode of Neural Information Retrieval. Today's a really special day because it's the first day we are recording these from the new offices of Zeta Alpha, which are located in Lab 42, same building as Andrew is also now located. And for the first time, we have a guest that's also from Zeta Alpha, who's Marzieh Fadaee. Want to introduce yourself first?
Yeah, sure. I'm very glad. I've been listening to podcasts all the time, and I'm very glad to be on it finally. I'm Marzieh Fadaee. I'm the responsible person for doing research at Zeta Alpha, focusing on neural search in the past year.
Cool. My name, as usual, Sergi Castella. I'm an analyst at Zeta Alpha. We've been doing this podcast for close to a year now. And with me I have, of course, usual Andrew Yates.
Yep, I'm Andrew Yates, assistant professor of the IR lab here at University of Amsterdam.
So before we get into the meat of the topic, do you want to give us a little bit of your background in research, what you did in your PhD and what your journey is until now a little bit?
Yeah, sure. So I have been working on machine translation in particular during my PhD, but the focus was, and it was at the beginning of these deep neural models showing promise in the field of NLP. So looking at seeing how we can use deep models to improve the translation quality. I have actually worked also on doing data augmentation for machine translation in particular using language models. It was 2016, so before large language models, even before transformers. But I have seen that how data augmentation is actually really effective for improving the learning process of these tasks. And that's something that I've continued working on at Zeta Alpha as well.
Cool. So the topic that we wanted to discuss today, and the reason why we brought Marzieh in, is I would describe it as language models for data augmentation in information retrieval. I don't know if you agree with that title.
Yeah, I think that's a good, yeah.
So unlike in previous episodes where we've centered our discussion in one single paper, this time we're going to look at, we decided to look into two papers that do this, and the first one of them is InPars, Data Augmentation for Information Retrieval Using Large Language Models, of which Marzieh is one of the co-authors, and then a more recent paper that from people at Google called Promptagator, that has also been quite popular lately, that do a very similar method. I think one of the interesting parts of the introduction of the InPars paper is this reflection of what challenges there are in leveraging large language models in information retrieval. As in, I feel like the kind of impact of large language models has been is a little bit delayed in the field of information retrieval compared to other NLP tasks. Could you talk a little bit about that and reflect on that?
Yes, I think one obvious reason that it took some time to get to this point was just computational bottleneck of how in retrieval, if you want to encode everything, the pool of candidates is just too large to do that at inference time, because search is just looking at everything. And that was something that, so there has been some works battling this, trying to find ways around it. But also there has been some works on just scaling, with the improvements of scaling and computational power that has been going on in the most recent years. I think it's not really to the point that information retrieval is benefiting fully from advances in neural models, but it is at the point that there are still a lot to do there, but there has also been some really great works going on recently.
Yeah, I mean, I totally can see this thing of the delayed usage of neural models in information retrieval, and I think that we've previously joked about how, still today a lot of benchmarks are it's hard to beat BM25, right? In a lot of benchmarks and tasks.
So about the same question, I would like to know what do you think? So what are the...
I had the same thought. So efficiency. So there's a lot of candidates to consider. You can maybe get around this with re-ranking, like Mono T5, I think you use it in InPars. Yeah. There's some more recent work trying to do this a bit differently with T5, but you still are doing re-ranking, so many candidates to score. And then if you think about even a generative model, you might just have a lot of output. I don't know how this scales actually if you want to return 1,000 or 10,000 documents generatively. I don't think there's work doing this yet. But in both size scale, I think is the key challenge.
All right, so let's dive into a little bit more detail what the InPars paper proposed. So like, can you first give a little bit of a gist of the motivation and kind of like summarize the abstract of the paper for us?
So like we said, the bottleneck of computation is something that was also a motivation for this paper. So we were thinking about how to use the power of large language models that show promise in a lot of different fields in information retrieval as well, without actually using them directly during training or inference time, because it's costly, both computation-wise and also money-wise. And the idea that we had was, how about we use these large language models for generating the data that we need and we are missing for out-of-domain retrieval. And the data that we are missing is relevant queries for documents in different data sets. So it can be like in any domain, but usually these domains are like really particular, and the general purpose data sets that are available, like MSMARCO, they might not be a great fit to train a model for these data sets. So then the idea was how we can do that. So
if you so going back to the recording, so can you like give us like a recipe, like step by step kind of steps that you follow to generate these synthetic data or augmentations using a language model?
So we the target is different data sets that are in different domains. So for each data set, we want to generate a synthetic data that fits that data set. In order to do that, we use a prompt where we have 3 examples of query document pairs that we sampled from MSMARCO. And then we have the 4th example, which is just a document, unlabeled document, sampled from the training data, and then asking the language model to generate a query for that particular document. And we did experiment with 2 different types of prompt, which we can talk later about it. And essentially that's the prompt. Then the language model generates the query for the given 4th document, and we change that document by sampling again. In the end, what we did was generating a larger set of document query pairs, and then we actually had to filter some of them out, because just like the quality of synthetic data is not always perfect. So we tried with different metrics how to filter out, and in the end the best one was just to use the log probability that the language model gives to the query that it generates. So how nice and linguistic the query is essentially was our filtering method. So we picked the top pairs of document queries, the result of this filtering approach, and we use that to train a re-ranker. So this re-ranker is trained only on this data set, not any like previously labeled data set, so only on the synthetic data, and then evaluated on the same data set that we generated the synthetic data for.
So you generate basically 1 query per document, right?
Yeah, that's
the number. And the filtering numbers that appear in the paper is like you keep 10% of the generated query. So you have from 10,000 to 10. So we generate 100,000 synthetic queries, and then we filter it and select the 10,000 best ones for training the model. Okay.
Yeah.
And what model do you use? Language model do you use to generate?
So for these experiments, we used the OpenAI language models. We tried experimenting with different ones, and we ended up running all of the experiment with the Curie model, which is around 6 billion parameters. And we saw that the difference between this relatively small model with the much larger one, with I think the Da Vinci one with 100 something billion parameters, wasn't too much. So what we were gaining from using a smaller model it was enough for what we were doing.
Mm-hmm. Okay.
To that, so we did that by using a few-shot learning approach. I would say maybe almost zero-shot learning approach. Yeah. It's not really also few-shot. And we did that for the different data sets in the beer benchmark, generating these synthetic queries for documents, and then trained a re-ranker on this synthetic data. So not really using any other, like MSMARCO or anything like that.
I think, so you called it both few-shot and zero-shot. I think this is interesting and connects back to what you just said about having in-domain queries, because it depends on how you look at the domain, I think. If I understand correctly, you use MSMARCO always for the prompt. So the examples are just the MSMARCO question answering task. So in that sense, the queries are not in domain. However, you generate them from documents coming from the target collection you're interested in. And in this sense, the queries are in domain. So I don't mean I disagree with this characterization. It's a bit ambiguous, right?
Yeah.
And this is interesting. And I think this goes back to the zero-shot and few-shot.
Yeah, so it's not really like a clear line defining that. Yeah, indeed, that's true. So I think it was important for us that the distribution of the document, so the training data that we wanted to create, we wanted the distribution of the documents to be as close as possible to the domain that we are evaluating in. So the documents we decided to come from the data sets that we were evaluating on. We also did some ablation tests on whether we sampled from MSMARCO or from the documents themselves, or from the data sets themselves to see the difference. And we saw that in-domain sampling was better than just sampling from MSMARCO. But for the prompt, we didn't also want to do any prompt engineering, quote unquote. So you could essentially, do that also the same for the examples that you have in the prompt. But we try to stay away from modifying and optimizing the prompt too much. So we didn't want to go that route.
Okay, so let me rephrase it if I understand correctly. So you basically, with BM at retrieval time, you get a pool of 1,000 documents with BM25, right? From which only one of them is marked as relevant via this synthetic data labeling process, and then the re-ranker learns to rank that as the highest probability document.
Yeah, exactly. Right? The rest of the documents are the BM25 results, and no end actually. Yeah.
So okay, I think that it makes sense. Do you have any other comments to add?
No, just to point out, it's a standard re-ranking setup, but maybe one interesting observation is because you're doing re-ranking, you don't have to think about these hard negative mining techniques that are often used for dense retrieval, right? Mm-hmm. So you're always ranking BM25, so the negatives can be chosen from there. It simplifies things.
So I also had in the notes written this thing about but now I suddenly forgot about the QVP.
The prompts.
The QVP prompting.
Yeah, the good, bad.
Oh yeah, the good, bad question. So before we jump into the results, I think one of the interesting things that I would like to comment on is in figure 2, I think is a very nice example of that. You do the comparison of two types of prompting that's called vanilla prompting and GBQ prompting. Can you speak a little bit to like what that is, what effect it has in the generation process, and how you came up with that a little bit?
Yeah. So the vanilla one was the straightforward, like what you would do the first time that you want to create a prompt like this to generate the queries was coming from. And in the vanilla one, you just have like pairs of document queries that in this case we have 3 examples randomly sampled from MSMARCO training data. So we did some experiments with this prompt. What we were not really happy about was just like the quality of the synthetic queries that we were generating. And when we looked at the examples that we gave in the prompt, we also saw that it's not really the language model's fault. So if the query that we have as an example is just like a yes/no question query, or it's just like a query that the answer is just like one word in the document, so you don't really expect also to see very interesting questions that require knowing all of the information in the document. So then what we thought was, how about we tell the language model to distinguish between good types of queries and bad types of queries. And like good and bad, we use it here loosely, so it's not that like one is like really bad, but just in the sense that in our hypothesis, we thought that a good query is something that is more complex. So in order to answer that, you need to understand the document rather than just like extracting one word or one sentence from the document. And that is essentially also like down the road, because you want to learn good document representations. So if the answer comes from just one word, you also don't expect the model to trying to encode all of the information in the document in the representation. But if it's a more complex question, then the model has to work harder to encode the document information. So that was how we came up with the GBQ prompt. And what we did also here was that, because it is like a zero-shot learning, we just had these 3 examples for all data sets. We used the original queries from MSMARCO as the bad examples, and then we manually came up with better queries for these examples. So for the same documents, questions that are more complex.
So would it be like fair to call it a bit of like a kind of like hard negative prompting or something like that, in the sense that you're trying to like show them all kind of examples that are could be easily misunderstood as good or something.
Yeah, I would say so. Yeah, maybe like trying to like move away from these types of questions to more like these types of questions.
And is this also related to like the fact that you used a small model, or did you also observe this behavior of kind of getting bad synthetic queries with the larger model? As in, is this a crutch because you're using the query model, or this is also behavior that also with the large DaVinci?
Yeah, it was actually, we saw that with both models, we actually tried 3 different sizes, and with all of them we saw improvements, but the improvements was not, so like going from the small to medium to large, from medium to large, the improvements were not that significant anymore. So that's why we decided to just use the medium, the query model to do everything.
I would guess it's more of a problem with MSMARCO, because there are just some queries that are factoid, like single answer, very easy. And it's probably, you don't want to use these as prompts, right? You don't want to generate a query that can be answered in one word. So it's the input data largely, I think.
I'm also wondering, how much of a problem is it that, so when you train a re-ranker, you only have one document labeled as a positive, right? But like other works have shown, like when we commented on the shallow pooling of sparse labels, a lot of the other papers, right, that are on top are also happen to be relevant. They're just not annotated as such, right? So like, is this problem exactly analogous to when the annotations come from humans, or is it different when the annotations come from like from synthetic data, or like?
Yeah, that's a good question. I would say it's very similar, to be honest. I don't think it's...
I feel the same. I think it is pretty similar.
Yeah, because so like again in this like synthetic generation, you only look at one document, you generate one query for it. So you don't really look at the other documents in the ranked list. And it might as well be that those are also like, then you search for that query, you get other documents that are relevant, and those might also be correct answers for that query, especially also when you do re-ranking. So like the BM25 step might already retrieving like a lot of relevant documents anyway. So I think that's more maybe a challenge or question for how in general we do these evaluations with this like just one annotated relevant query and like the rest unannotated. But it's also different so we evaluated on different data sets, and the number of annotations that you have per query are different from data set to data set. So the ones that have more annotations, then you can maybe trust the results more because you don't have the problem of unannotated documents in your results that might be relevant.
And lastly, before we jump into the results section, you kind of mentioned that you didn't do a lot of prompt engineering or prompt tuning. Can you like describe a little bit how what that means? Because you certainly tried a couple of different things. Like to what degree? How much time did you spend optimizing that? How much better do you think you could get this method to perform if you actually did a lot of these kind of latest tricks in prompt engineering?
So for our experiments, the 3 examples that you see in the paper in the prompts were the first ones that we sampled from MSMARCO. So we didn't try to see how with different samplings the result might be different. Honestly, because it's also expensive how we do things, right? With every new prompt, you had to generate synthetic data for every data set that you're evaluating on, and then evaluate and see whether it works or not. And then with the vanilla prompt, we saw how the synthetic data was looking, and then coming up with a more elaborate prompt to address this issue was also a more or less like a one-time try. So we changed the original prompt into this format with the good question, bad question pairs, and that was it. And I would say that it's not obviously the first thing that you try is not going to be the optimum one. So how we formulate the good question, just how important these 3 documents are, document queries are that we sample. Because also we see in a lot of papers, especially recently on chain of thought reasoning, how sample selection for prompt is important. That is something that they actually look into. So yeah, definitely there are rooms for improvement in all of these cases. Also how just a new way of formulating this prompt to generate synthetic data. But what we did in our experiment was not really exploring that area, but rather going with the intuitive prompt, trying to generate the synthetic data and see how we can filter out and find the best ones and use them in our evaluation.
So correct me if I'm wrong, but I get the feeling that part of the reason you maybe didn't optimize that much is because, as you said before, it works so well from the so early on, quote unquote, that you didn't need to squeeze a lot of the performance from optimizing that.
Yeah, so that was one reason, and second was cost, just running the whole thing again.
Actually, can you give us a ballpark of how much it costs to generate per token and per data set or something like that, or?
Yeah, so we ended up using the Curie model, 6 billion parameters for all of the experiments, and it costs around $100 to $300 to generate 100,000 samples regardless of the prompt. So both prompts would work the same. And we do that, we generate 100,000 queries per data set in the beer benchmark that we evaluate on.
All right, so that said, let's jump into the evaluation section. First, can you give us a bit of an overview of the data sets you use and maybe why? Maybe better focus on why you use these benchmarks, because some of them, MSMARCO, track, we've talked about in the past, and our audience is probably familiar with them.
So our goal was to improve zero-shot retrieval for out-of-domain scenarios. So beer benchmark is a good benchmark that contains how many? I think 18, 20 data sets that are like in different domains, widely varied from each other, and it's a good start for evaluating a zero-shot approach, and that's what we did. So we started from beer benchmark. We selected some of the data sets from that because running on all of that was costly. But the data sets that we selected, we tried to have a variation of just like really different domains and also really different in terms of the sizes and the number of annotations that they have per query. So we ended up, of course, evaluating on MSMARCO, which would count as our in-domain evaluation, but then also evaluating on the TREC DL dataset, the Robust 04, natural questions, and the TREC COVID one. Okay,
so I think we can just go into the table 1 main results. So first, can you also quickly mention the baselines that you compare your models against?
Yeah, so, well, the BM25 is the obvious benchmark that, the obvious baseline that we want to compare with. But there has been several works on out-of-domain retrieval problem more recently, 2021, 22. So there was a Contriver model. There was also the paper from OpenAI that used the same language models that actually we use for synthetic data generation, but they use these language models for actually training and inference. So it was just like the encoders that they use to do retrieval was initiated with these language models. Which for us, if we wanted to do that, it would be really costly, but for them, it's doable. And then we have our own approach. And we saw improvements in almost all, I think, all of the data sets that we evaluated on.
We have a professional table narrator.
So I'll take you through table 1. We have some unsupervised methods like BM25, Contriver's Dense Retrieval, I believe, with this span overlapping pre-training, CPT text, also Dense Retrieval. There's some baselines using OpenAI's search re-ranking API, I guess. So these are using the same model that this work is using to augment data, but using it directly for search. So like Curie, we've been mentioning 6 billion, DaVinci is 175 billion parameters, and then also a smaller Ada, 300 million parameters. Then there's this work using data augmentation. So for those models, it's Mono T5 is trained with data augmentation to re-rank BM25. Optionally also trained, pre-fine-tuned, I guess we can say, on MSMARCO before this training. So we see with and without that pre-fine-tuning. And then some supervised baselines. So these, I believe, are trained directly on the target data. So for example, this same Mono T5 re-ranker, but trained using the human labels rather than the data augmentation. And in this supervised category, we also have a few other baselines like Colbert V2 that we've talked about before. GPL is another data augmentation method, MiniLM, Contriver, and so on.
Can I maybe just add here? So the supervised one, we pick the same or use the same models. We fine-tune on MSMARCO, and then we fine-tune on our synthetic data.
Right, yeah.
So
that's a good, yeah.
That's a distinction, like how much like a general purpose MSMARCO type of data set can add to this out-of-domain evaluation.
Can you repeat that?
When training, we have this option of whether we start from a checkpoint that's been trained for the relevance task on MSMARCO, or if we just start from the actual model checkpoint we were given. Mm-hmm. So for InPars, they look at both of these. So they look at InPars trained directly on the augmented data, or InPars first trained on MSMARCO, then trained on the augmented data. The supervised methods being compared with here follow this latter setup. So they're first trained on MSMARCO, or pre-fine-tuned, I guess you could say, and then fine-tuned on the supervised data.
If there is supervised data.
Right.
Exactly. That was what I was gonna ask. So, or clarify. A lot of the entries in the supervised category are empty because there's no supervised data set for those tasks.
Well, it was mostly because they didn't report it in their paper, so we don't have it there. But the main, I think, one point from this paper that you can infer is that when you, because for so long the MSMARCO dataset was this general purpose large dataset, and even with creating smaller datasets, you would maybe argue that, okay, maybe having a much larger one is still more useful if you have just small annotations, and you can still benefit from that. The supervised section of this dataset, they use, the supervised section of this table, they use MSMARCO in various ways depending on their approaches. And in contrast with just not using MSMARCO and just using synthetic data, which is smaller and automatically generated, but in domain. So that's the main distinction. With MSMARCO, we wanted to show that it is important to have that, even though MSMARCO, of course, add to the gains that we see in these approaches. Still, that synthetic data that is in domain is important to have, and it's worth investing on to create. And I think it's also a nice case to show that if you compare line 5 and line 7, for instance, or line 8, our approach in this table, the Curie model is the same model that we use to generate synthetic data. So there's this really large, medium-sized, but relatively large language model that you can either use that, plug it into your neural retrieval and re-ranker, or you can just use it in an offline setting to generate some data in a small scale, and then use that to train your model. And we saw how different the performance is. So as nice as it is to always work with these really large models, I think it is also important how we use them, how we incorporate what knowledge they have into the downstream task that we want to improve and evaluate on.
Is there any other is there any other bits that you'd like to highlight from this experimental section, or other kind of takeaways that you would get from it?
So I think a really high-level thing is that InPars is usually about as good, maybe slightly better, maybe a bit worse than the supervised methods. Obviously not, as we said, there's not a comparison point for every supervised method for every data set, but where there exists comparison points, InPars performs quite well in comparison to them. I'm referring to the InPars where with MSMARCO followed by the augmented data. I guess that's a good point to point out that if we look at InPars without this MSMARCO pre-fine-tuning, the results are a bit worse across the board, a bigger drop than comparing supervised versus InPars, but it still works. It benefits from that MSMARCO data, but it's not that you absolutely must have it, I guess is one way to say it.
Yeah, that's completely correct. And I would also add to that I think this paper shows the importance of working in domain specificity that comes with each domain is important, and having that in your data is important. And I think that's something that the Promptagator paper actually looks at it a bit more, with how it creates different prompts for different data sets, which we didn't do in this work. But as much fascinating and maybe enticing it is to just use huge amount of general purpose data to train these models. At the end of the day, that specificity that comes into play with the in-domain is something that still has value and still adds to the whole learning process.
So something that, I don't know if you already mentioned this, but I just realized I didn't understand something, is after you pre-train on MSMARCO, do you have different models that you fine-tune on each one of those, or you fine-tune a large model on all of those combined and test one model on all of the tasks?
So we train or fine-tune models per data set with the synthetic data for that data set. We did actually, as a follow-up, not in this paper, tried combining all data sets, fine-tuning one model on all of it, and it didn't work as well.
Interesting. With a model the same size, or do you try also with bigger?
Well, with both variations of Mono T5. Yeah.
Okay. Well, that's interesting. Okay, I think that it would be interesting before we jump into what the Promptagator improves on. If we comment briefly on the ablation studies. So, so do you want to quickly comment on the table 2 for ablations?
Yeah.
Right. So with regards to ablations, we're not going to cover everything, but let's just quickly look into table 2. So maybe Andrew can give a quick description for the listeners.
Yeah, so in table 2, we have an ablation of the prompting setup. So you'll recall the prompt consists of 3 query document pairs, document, good query, bad query, and then a 4th document where the model is asked to complete the good query. So what the prompting is, what's being ablated here is whether that 4th document comes from the target domain or from MSMARCO. So basically this is saying if your training data is coming from your target corpus or just coming from MSMARCO in general. That's one of the 2 things ablated here. The second is whether you have the separation of good and bad queries. So you could have good query colon the good query, bad query colon a more factoid query, or you could just have query colon some query. So they're looking at these 2 dimensions, whether you're just generating a vanilla query, as it's called here, or with this good-bad query decomposition. So this table is looking at basically combinations of those with the Mono T5 models.
And what we saw was that, so we talked about the importance of having in-domain queries for these data sets, but we also see that it's not universal across different data sets. So when it is out of domain, we have the MSMARCO, and if the data set is somehow close in distribution to MSMARCO, it actually still works better if the input documents for the fourth section, for the fourth document that we want to generate query for comes from MSMARCO. But something like track COVID, which is just like MSMARCO doesn't know about COVID, so it's like the distribution of documents there is completely different. So for that data set in particular, the in-domain using in-domain documents is actually more useful than using MSMARCO as input documents.
And if I understand correctly, if you compare 1 to 2 or 3 to 4 on the MSMARCO MRR, the only difference is that you add more synthetic data versus only having the MSMARCO data, or that you add the data with the GBQ prompting?
So actually in both cases, so 1 and 2 and 3 and 4, we are evaluating here on the synthetic data that we generate. But if you remember, in the vanilla prompt, the queries are from MSMARCO, so like the queries that we also generate are similar to the queries in MSMARCO. And with the GBQ prompt, we want to get away from this. And when we evaluate on MSMARCO, we see that actually happens. So synthetic data that generated from vanilla prompt is actually more successful on MSMARCO because the distribution of queries are closer.
I see, but this is not comparing it to only training on MSMARCO data?
No, in this table
right?
there is no.
Okay.
Yeah.
And would it actually hurt, or would it improve only on MSMARCO when you add this? Because it's maybe something that you checked in table 1, but I missed.
So like,
you know what I mean? If you only use labeled data from MSMARCO versus if you use labeled data from MSMARCO plus synthetic data on MSMARCO.
So I think, I'm not sure, so that's something that I have to check, but in table 1, line 14 and 15 would be like the same re-rankers that we used, but only trained on MSMARCO.
I see.
Not really on in-domain.
So then it would be indeed a little bit, it improves a little bit.
Yeah.
I mean, marginally, but I see. Okay, yeah, then it makes, I just had, for a second, I thought that adding synthetic data was hurting performance, which I found surprising, but it seems like it just stays on.
Yeah.
Okay, that's it. I think that, is there anything else you would like to mention before we jump into the Promptagator?
I think we can move on to Promptagator.
Yeah. All right. So let's move on to the Promptagator. So this is a paper that's quite similar, right, to what InPars does. It's a little bit more recent, but it's a little bit more successful in some evaluation settings. So I don't think we should go into all of the details of the paper because there's so much overlap. So I think it would be useful Marzieh, can you describe maybe what the paper does and focus specifically on what bits are different from InPars?
So this Promptagator is a really nice work that came out recently, and the ideas are similar to InPars, so how we can generate synthetic data for datasets that we don't have maybe in-domain data for, and using large language models for that. So there are, of course, some differences between the InPars paper and this work. So one very clear one maybe is that the model that they use. So in the InPars, we use the query with 6 billion parameters. In this work, they use the FLAN model, the larger one. They also sample 8 examples per data set rather than the 3 examples that we had. But there's also some differences in how they sample that. So they do that per data set, so these few shots actually change from data set to data set in their prompt. And they also sometimes look at the depth set for these data sets to sample these for, which, you can argue that maybe it's not...
So I guess this relates to what you said about, right, that you could argue that the InPars method is zero shot in a sense, that it only uses, it always uses MSMARCO samples in the prompt and not task specific prompts, whereas here they do use the task specific examples in the prompt, so that would make it closer to few shots.
Yeah, that's how I would view it. So they talk about query intent here, which is really just closely tied to the task. And I view this paper as adding query intent. So the example I always use, they have this argue-ANA corpus in beer. The goal of argue-ANA is to take a query and find the counter argument to that query. That's a super specific query intent or task, right? That's not normal general search.
Yeah.
So they're adding this in. So they have some knowledge of, for example, the argue-ANA, you're supposed to look for the counter argument rather than anything that seems relevant to this argument you input as a query. So to me, I would call this few shot because you have some human labeled examples from the target data that show you here's a real query and here's a real document relevant to it. If I go back and think about InPars, I don't think you need to do anything. There's no human involvement that's new needed. So if you're going to index some documents, you could also run this InPars thing as part of whatever you're doing to create your document collection. There's no human labels that have to come in. I guess there's different senses of zero shot and few shot, but this is to me the most helpful with these specific papers.
Yeah, no, that makes sense. And so, like, one of the also problems with this, like, out-of-domain evaluation is sometimes we don't have any labels, like we have 0 training data. And for InPars, like you said, that's no problem. For an approach like Promptagator, they look at the test set to select their few shot examples in their prompts to generate synthetic data, which, to be fair, they also exclude those test sets from evaluations, even if they do good on them. So they just say that they failed on those, which is good. But you can also argue that they are looking at the distribution of test set in the few shot samples that they have. Like, what is the impact of that? That's questionable.
Yeah, so I think they always use 8 samples.
Yeah.
So it's not a huge number, but it does characterize the task.
So I'm not sure I understood properly. So they use 8 samples from the test set in the prompt to generate.
Or from the train data. But if there is no, some data sets they have no train data.
Okay, so then they use.
So they have no queries essentially in the train data. So then I see. Yeah, and 8 is not a lot. Yeah, that's true. Yeah.
No, but I really like the kind of like the way of seeing it, as you said, as in if you have, as in like the InPars method is something that you can kind of like inject in some kind of pipeline for processing document collection, right? As like whatever that is. Whereas in this, in Promptagator, you need to curate a prompt per domain. So like if you have a new kind of like domain of document collection that you want to index in your neural search index, you need some human input, right? So it's not fully.
Yeah.
In that sense, it's few shot compared to the InPars.
Yeah. And maybe adding to one of the other main differences, I think, is where the number of parameters are in InPars and Promptagator. So we have the stage that we generate synthetic data using a language model, and then we have the stage of retrieval or re-ranking. And in InPars, we use a relatively small language model with 6 billion parameters to generate synthetic data. And then we use a much larger, smaller but also larger re-ranker to do the retrieval and re-ranking. For Promptagator, it's almost the other way around. So they use a much larger language model to generate synthetic data, so the large FLAN model, but then they use I think 110 million parameter model for retrieval and re-ranker, so a smaller model for the second stage that they do. Another thing that is, I think it makes a big difference, is just like the scale of synthetic data that is generated. So in InPars, the re-rankers are trained with 10,000 samples in the end. With Promptagator, they generate, I think, up to 1 million samples, and per document, they also generate multiple queries rather than one queries that we had in InPars. And that also changes the scale of the experiments.
Mm-hmm. So do we have actually maybe even when we go into the results, how much of a explanation is provided for these choices, right? It seems like a pretty important choice how you distribute your say the parameter budget between the synthetic data generation and the re-ranker. Do they actually have this?
I don't think they explicitly say. I think just because they have access to large FLAN and it's not really that costly for them, so they went with that one.
Yeah.
And probably also generating higher quality synthetic data just because the language model is larger. I'm not sure if they also tried with larger, they don't report it in the paper whether they work with larger retrieval and re-ranker, but with just this small one, the results that they get is already really nice. So maybe they also didn't really feel the need to play with much larger models in that stage.
So as I understand, one of the differences between InPars and Promptagator is the retriever, right? So in a re-ranker, you have the retriever stage and then the re-ranking stage. So how do they do that in Promptagator? How do they do that, and how does that relate to filtering, which I think that is also like all mesh. I think it's a very interesting.
So I think the filtering is done by first training the dense retrieval model with their augmented data. then feeding this augmented data or this generated data back into the model, and then given a query, checking whether the relevant document appears in the top K. If it doesn't, so it's not returned highly, then they throw out this query pair. Is their consistency filtering, they call it. I think I missed part of the question.
No, I think that makes sense. No, it's just I didn't realize it would work like that. It's mind blowing actually. So you basically generate you train the dense retriever, and of course you have to throw away the ones where the dense retriever doesn't. But you would expect that if you train the dense retriever long enough, all of them should appear. I mean, I guess because it's like kind of like using bootstrapping your kind of like metric as your target.
Yeah, if they had a large enough model and they train long enough, it should just always place it at top 1. But it's a smaller model, like it's 110 million parameters, I think. So it's not massive, and I assume they know not to train it.
Yeah. So like it's a feature that it kind of like underfits it doesn't. Okay, that's very interesting. So they don't throw away anything based on log probabilities, right? As you did in...
Which I think is actually smart. So if you think about the objective of retrieval, whether a query is good or bad, I mean, like linguistically, it is also important to have like a nice query, but it is also maybe more important to evaluate a query as good or bad with respect to the relevant document and how you can whether retrieve it or not, or how close it is to that one. So I think that's a nice way of doing that. That they also call it, I think, unintuitive, but it works, so it's really nice.
So actually, that's a very good point. So what kind of biases do you observe when you do this filtering? As in, when you do like generation of so many queries and you only keep the high log probability, like do you have any intuitive understanding of like what that means in human terms?
It may affect the length.
Yeah, definitely, because it's just like problem. That's one thing. But also, like if you think of just like two different very similar sentences, that one maybe just has like one typo, or just like it doesn't have like the final question mark than that the other one has. So the language model would prefer one of them, but maybe the other one would be better for retrieval, not really like having a perfect sentence.
Yeah, you probably don't get things like keyword queries, I would guess. It probably looks like natural language.
But that is actually a good side effect. Right?
Which matches,
So you don't want short keyword queries, but you also want relevant queries, not just good questions.
And actually, maybe this I should have asked this question before, but how much of this filtering is necessary because you're using the smaller model instead of the big model? When after you're using the QB prompting, as in, shouldn't all of, you know what I mean? Like, shouldn't all of the queries generated be pretty good by then, or?
Yeah, they weren't. So we ended up needing the filtering. We actually did run the experiments, I think not on all data sets, but on Trek COVID definitely, and I think Robust 4, with also evaluating just using everything that we generate as synthetic data. And it was actually performing worse than using the top 10% that we filter out. So it seems like there are some noise there, that maybe not noise really from semantically and syntactically wrong queries, but maybe queries that with respect to the document, they were not really relevant, or the model wasn't really learning from them.
That's very interesting. I feel like you kind of, it seems to me like you mentioned this as in like the filtering is, you're almost apologetic about the filtering, as in it's very much a crutch that shouldn't be there, but it kind of works. So
because also
forced.
we are just like in general we are arguing about how more data is better, how even like synthetic data, even when it's noisy, it's better. It's also with Promptagator paper. But in both papers, we also see that filtering is important. So not really using everything that you generate.
Yeah. No, it's a very good. So anything else to add?
Don't think so.
Okay, so let's just check the results of the Promptagator, which I believe are a bit better than InPars, but again, they're not really comparable in this kind of zero few shot sense. So let's just quickly look at table 2. Maybe you can give a quick description of that.
Yep, so we have 2 high-level groups here. One is just doing first-stage retrieval. The other is doing first-stage retrieval plus re-ranking. I guess we'll look at first-stage retrieval first. A few baselines. So we have the standard unsupervised baselines, BM25 and Contriever as an InPars. And then we have some supervised baselines that I believe are trained only on MSMARCO. Is that your understanding also?
Yeah.
Yep. So these are, for example, Splayed V2, Colbert V2, we've mentioned before, some augmentation like GenQ, GPL, also GTR, XXL. And then Promptagator in both a zero-shot and a few-shot configuration. So few-shot would use these 8 examples from the target data set, and zero-shot would not. So I guess one key finding from this, the top section, the first stage retrieval part, few-shot does help quite a bit. So going from like a 45.5 to a 47.8 average on beer. Also on individual data sets, there's an improvement, but we don't want to read all the numbers. Averaging is not necessarily the best way to look at it. If you compare against like Splayed, for example, though, it's not a huge, there's an improvement, but Splayed, for example, sits about halfway between the zero-shot Promptagator and the few-shot Promptagator. So 45.5, 46.6, 47.8. So it is improving over Splayed, but it's not completely, making it obsolete, maybe is one way to say it. But then if we look at the second group, which I think is the more interesting one, where we have a re-ranking step on top of that first stage retrieval, we see, big additional improvements from that re-ranking step. So here, baselines include InPars, but only for one data set, Trek COVID. This mono T5 model we were looking at in InPars, I think, is the main baseline. This is trained on MSMARCO again. And then what they call Promptagator++, which is just with this re-ranking step on top of the first stage retrieval. The story is the same between zero-shot and few-shot. There's, again, a good improvement moving from zero to few-shot. And I guess, again, you could say that mono T5 sits about halfway in between the zero-shot Promptagator++ and the few-shot Promptagator++. So like 49.9, 51.1, 52.8. So no, it's actually closer to, it's roughly in between. Let's not worry too much. So the point being, it outperforms the baselines. The few-shot setting seems to help. Anything else we should add?
No, I think that's a good summary of this table. So I just want to add that, especially like in these sorts of experiments, that the number of parameters might be also a bit misleading. Like the final model might be small, but it has also used a much larger model in generating the synthetic data. So maybe in terms of practicality, if someone wants to use the same approach, they should also take that into account. But yes, with how they had this like specific prompts per data sets and how they generate this synthetic data, they do show that it is, especially like in an unsupervised, compared with unsupervised approaches, they show really nice improvements.
Yeah. Maybe one additional fun thing to point out. So there's only one comparison point with InPars, which is Trek COVID. On that comparison point, Trek COVID with InPars is higher than with Promptagator few-shot. But this is just one specific.
I didn't want to mention that.
Yeah, I thought I would point it out for you.
So there's this line below Promptagator, both in the retriever and retriever plus re-ranker settings where it says zero-shot. So what does that mean?
Yeah, this is a good question, and it gets back to our earlier zero-shot, few-shot component discussion. So here, zero-shot means they just have a very simple prompt. It's read the passage and generate a query. So here, zero shot, they just have read the passage, generate a query. In parse zero shot, they have some examples of queries generated from passages. So this is a bit stronger, but still, I would say zero shot. And then few shot here, they have exact queries and passages from the target data.
Okay.
So
we might need a new nomenclature for something in between zero shot
we
and
have
few shot.
quite a continuum here.
So I guess like the main gist of it is like we were saying before, InPars and these methods are not like very similar in spirit of but are not really that comparable in terms of performance because of these zero versus few shot, and like it feels like Promptagator has the kind of a stronger few shot and then kind of more advantageous few shot, and InPars kind of sits a little bit in between because it uses MSMARCO documents in the prompt.
Yeah. So there's differences like FLAN, the larger model used here. If there weren't those differences, what I would say is this shows you how much learning the query intent or learning the task can do. But that's not exactly what it shows because there's also other differences. But maybe it's kind of hinting in that direction. Yeah. Here's what you get if you can specialize to the task specifically. But also tangled up in the other changes.
No, I think that's definitely true. So besides very implicitly in our experiments in the ablation test in InPars that the table 2 there where we whether the input comes from MSMARCO or the in-domain data, how like the data sets that are closer in distribution to MSMARCO, they have better performance if the input data is from MSMARCO, and the data sets like track COVID that is different, its in-domain is better. So that was like a very implicit way of like the importance of the query intent or the distribution of the data and the impact of that. So I think in that sense, it's a nice validation that when we are looking at these out-of-domain data sets, it is good to look at what they're actually trying to answer, like the Arguana data set that is like really different than retrieval, and trying to make everything work with that intent.
Yeah. Mm-hmm. Another fun example, they also have DBpedia entity search, and this is quite different. I believe you just are supposed to return like some entity name. So I think this is correspond to something like a Wikipedia page title. So, again, there's many flavors of query intent here.
That's very interesting because I feel like when I think of information retrieval, kind of just go to the kind of Google type of query and then documents, and you don't think about all of these other task intents, which are very much also part of information retrieval.
Yeah.
That said, do you want to comment on some of the ablations that Promptagator shows, or?
So one maybe is this consistency filter, because we talked about it a bit. So they have a figure 2A, the far left, basically just showing, if I follow correctly, the impact of doing this consistency filtering. And so it usually helps. There's a few data sets, it hurts a little bit, so like maybe a 1.4 decrease. But there are more that it helps substantially, like a 7, 6, 5, 3, 3, 2 increases. This is a difference in NDCG. I guess this isn't normalized by the whatever NDCG we're looking at, but the point being, this seems to help. It doesn't really hurt much in any place.
Yeah.
So despite being unintuitive, it seems it helps.
To do this filtering loop that
this consistent training the model and then seeing if it returns the query again.
What I don't quite understand is how would you train a re-ranker without doing that?
So I think this is first stage retrieval.
Oh, only first stage retrieval. I see.
I'm not certain if they apply it to both, actually.
The consistency filtering. I think it's like a separate. It's not really like you do the consistency filtering, then you get your set of synthetic data, and then you use that to train your retriever or re-ranker. That was my impression.
I see, and
but then it's not. You need that to train the re-ranker, right? You don't need to do the consistency filtering to train the dense retriever, but for the re-ranker, otherwise you would get some samples where there's no positive document in the pool of documents to re-rank.
So I think this gets at the question of when you train a re-ranker, if your positive examples have to be returned by the first stage retriever. I think people normally make the assumption that the positives don't have to be returned by first stage, but negatives are sampled from what first stage returns. But this can differ. I've seen it done both ways.
I see what you mean.
Yeah,
so you basically, if it's not there, you just throw the document in the second stage.
Yeah.
Basically, kind of inject it.
Yeah.
Because you're just doing training.
Right. You're always training. I mean, either pointwise or pairwise or some small list.
So,
right?
so I guess like
always...
when you're training, it's only a matter of like the dense retriever is just a negative sampling, right? When you're training.
Strategy. Yeah.
I see. Okay. Yeah, of course. And then it makes sense that you would.
So you could either way.
You could do the whole thing without the filtering. Yeah. Okay, understood. It still blows a little bit my mind.
I'm not totally sure what it's doing. I mean, is it throwing out outliers or? Because also I've found they set k equal to 1, so it is if it's not the top ranked, they just throw it out.
K
equals
top k of 1.
Yeah.
Oh wow.
For the round trip filtering.
Oh, I see. Okay, yeah. Of course, in my head I was imagining more like 100 or 1,000.
I thought so too. It's a
little bit arbitrary, right? Because like depending on how much you optimize your first stage retriever on these. Like if the dense retriever is big enough, eventually all of them are gonna be good, right? So all of them are gonna be top. So
it's like a catch-22.
Yeah, it's a catch-22.
A good dense retriever you already have.
The catch-22. So like you're kind of like basically calibrating how much you optimize your dense retrieval. That's how you calibrate your filtering kind of threshold or something like that.
I mean, it's something like, given a model of this size and without training too much, does the query look like this document so much that it's easy to memorize it goes with this document? Is it one? I don't know if that's the only or the right way to look at it, right? But it's saying things you can really easy memorize are the ones we want to keep, which I guess somehow there's some coherence between. I don't know. It is pretty weird. Because I mean, that's basically what they're doing, right? They're saying if it can memorize that this query document go together.
I guess.
Or just like the synthetic query that they generate is so good that it like out of everything, it only like it retrieves the relevant document as the top one.
Yeah.
So it's because
but the thing, right? There's how good the query is and how good the retriever is.
Right, and
those two things kind of.
Yeah, what does so good mean as you're training the retriever? Like this. I don't know. It's something unintuitive, as they say.
I guess we'll have to email the authors. But nonetheless, I do think it's kind of one of the interesting implementation quirks of this. All right. That said, let's just jump into the final section and wrap up this conversation. I guess so. My first question would be like, how close does this method, do you think, gets us to the point where you have this very much kind of pipeline agnostic indexing of documents, right? Like you have a BM25, you just throw whatever you have in, and it just works magically. So how close do you think we are to that, and how much do you think this data augmentation, like synthetic data with language models, gets there?
So if anything, I think it actually shows us that we have to look into data from time to time, like how the query intent is important, how what are the type of documents we are trying to retrieve, what types of questions we usually get, and making it specific to different data sets rather than having one model that knows it all, is shown to be working better both in InPars and Promptagator papers. So getting to that point of just agnostic one pipeline for everything I don't think we are, at least in this line of work, we are heading in that direction, to be honest.
Mm-hmm.
So like depending on the data and what it requires, you might want to treat it differently.
Yeah, but
was that your question, or maybe not?
Sort of. I guess it's like I would say that you can have like multiple kind of verticals or like different models for the same data, but that still counts as kind of like one. I guess like maybe rephrasing the question is like, how close does this get us to good black box neural ranking? As in black box, as in you don't need to understand much of what's going on there. You just kind of like give documents and then you get a good retriever from there or something like that.
Yeah, I think it's definitely a step in this black box direction. So I guess I would kind of summarize what I said earlier. If you bring me a document collection, you could run InPars on it. You need a human to pay for it, but not to label anything, right? GPT. You could run InPars on it, and then you could train it without any additional human labels. So in that sense, you could have some, turnkey solution where you press a button and it does all this on that collection, and now you have good re-ranking search on that collection, I think. If you think about Promptagator, it's still somewhat close to that, I would say, because you only need some characterization of your task. 8 examples is not a lot to characterize some unique task, right? If you really care about it, you can write 8 examples pretty easily.
Yeah.
But I guess you still need the examples. So it seems like it's improving what we can do in this black box setting, right? It's data augmentation can improve how well you handle a document collection that you don't have training data for, I suppose. Mm-hmm. Is that?
Yeah, I agree. Yeah.
All right. So what do you think were, in your experience, what are the biggest limitations or on using synthetic data that comes from language models in this context, or maybe even not in this context, but also in other contexts? Like what is?
Yeah. So like you said, like we see more and more how data is important, and we also see that how relevant and good type of data is important. So you have like access large language models to everything on the internet, but having that like specific data for the task that you want to solve is, at the end of the day, is more important than just having huge amount of unlabeled data or general purpose data. And curating that data is important. So when we talk about curating and creating that data, then the challenge is either like manual labor that you have to do or augmentation. And the goal is to have this really nice, as close as possible to human annotations when we work with synthetic data. And that's something that I would say is still a challenge there. So we see in both of these papers how filtering is important. So that means that even with really nice language models, we are all every day impressed with what they can do, but they can still maybe generate things that are not really useful for the task. And that would be like one of the main bottlenecks, like defining what is a good data. So that's something that comes from our human perspective, and also being able to generate that with these models.
All right. So I think that to close this conversation, is there any what future directions, without revealing too much of your current work, of course, what future kind of broad directions in this space are you kind of excited about, or would you bet on?
Something that I think is interesting, I don't know that I would bet on it, but Promptagator, you have specific examples. Here's query from the domain, here's document from the domain. What if instead you had a task description rather than creating examples that indicate the task, and you pair that task description with query and documents that don't illustrate the task? Right? That would be one step further in making it easy to adapt to a new task. I wouldn't bet on that being easy to do, but I think it would be cool if someone were to do it.
Yeah, I was actually thinking something similar, how like we know these language models can generate the data, or they can get close to generate the data that we want, but how we communicate with them what we need, like that prompt, how we design that without really going into like the rabbit hole of prompt engineering. to get to that point, I think that's still something to explore.
Yeah.
But isn't that more on the language model side of kind of optimization, as in like making them, or do you see it more as a problem of like learning how to kind of nudge the model to? Because I mean, I my understanding is like it sounds a little bit like you don't really it's not satisfactory, the prompt engineering solution, right? So you kind of
For some.
my sense is that you don't find it satisfying, right? So you don't kind of like to optimize too much on that. So I lost my thread of thought, but isn't that then a problem of the kind of large language models to solve?
Well, I would say maybe yes and no. So we know these language models are really powerful. We know having relevant data is good to learning these models. And like the question of how to use the information inside these language models to get to that data. So like data augmentation is also like one example of that. It might end up getting to that point of like really trying to optimize for how or what these language models can do. But I would argue that it's with an intent of using that for a downstream task. So not really necessarily really doing anything or improving the language models, but finding the best way of using that in the pipeline of, in this case, neural retrieval.
I think this is a really good point to end the conversation. Thank you very much for listening or watching, and we'll see you in the next one.
Yeah, thank you.